Today I'm going to talk about, again, our goal is to understand this virtual Haken question. And today is mostly going to be a discussion of geometric group theory. So recall our goal is to explain these four questions of Thurston from 1982 about three manifolds and having to do with finite sheeted covers. Now I haven't explained all the terms on here yet, so again the goal today will be to explain these terms. I didn't get to some of the things I was planning on getting to yesterday, so we still haven't explained what these questions mean. So the first question in particular, I haven't explained what lerf means, but I think the other three questions I've defined at least what these questions mean. So the plan for today's lecture then will be to discuss some properties of three manifold fundamental groups. So I'll use the abbreviation sometime as a three manifold group to mean the fundamental group of the three manifold. And then connections between these group theoretic properties and these virtual properties of three manifolds that are underlying Thurston's questions. And then I'll start into discussing geometric group theory. What is geometric group theory? And again, this is going to be a very, not at all a survey of geometric group theory, but just to give you a little bit of flavor of it and focus on the concepts that I need for understanding these questions, which are generally have to do with ideas of Gromov in geometric group theory. So we'll talk about hyperbolic groups, cat-zero cube complexes, and right-angled arc groups and special cube complexes. And I might not get through all this today, in which case we'll continue talking about this tomorrow. And then tomorrow we'll fit these together to show how a certain problem in geometric group theory that was postulated by Donnie Wise last year, or actually his preprints a few years old, but he didn't really disseminate it until last year. So anyways, this conjecture that why it implies a virtual Haken conjecture, and then maybe I'll say something about the proof of the conjecture. Okay, so today we want to understand some geometric group theory, but first we're going to just do some general group theoretic properties. So groups residually finite, if every non-trivial element in the group, there's a homomorphism to a finite group such that that element is distinguished from the identity in that finite quotient. So it's residually finite if you can separate any element from the identity in a finite quotient. Another way of saying it is that the trivial subgroup is an intersection over all finite index subgroups of the group. So it's not hard to see the equivalence of these by the action of cosets on finite index subgroups. So examples include finally generated linear groups. That was originally proved by Malchev. And three manifold groups. So this follows, well, this was proven by Hempel in the 80s for manifolds satisfying the geometrization conjecture. So together with the geometrization theorem, this implies three manifold groups are linear. So that was not linear, but residually finite. The linearity question for three manifold groups is still open, actually, in the general. It's known for most classes of three manifolds now, but. And then mapping class groups of surfaces was proved by Grossman in the 70s that these are residually finite. So I wanted to talk about an extension of the notion of residual finiteness, which is called locally extended residual finite. So a subgroup is L in G is called separable if for all elements which are not in the subgroup, there's a homomorphism to a finite group which distinguishes that element, which separates that element from the finite group. So we can find a homomorphism to finite group K such that phi of G is not contained in the image of L. Alternatively, you can say it in a way that L is the intersection over all finite index subgroups H of G which contain L. So residual finiteness then is equivalent to saying that the trivial subgroup is separable inside of the group. So this is why it's an extension of residual finiteness, because we're extending it to other subgroups. Now, for example, in our, if we have a three manifold that fibers over the circle like we were discussing yesterday, then there's a short exact sequence of groups, the fundamental group of the surface to the fundamental group in the manifold injects to the fundamental group of the manifold and surjects onto Z. Then this subgroup is separable in pi 1m because, well, we can write it in this form. It's the intersection over, well, you take finite index subgroups of Z, which we know pretty well. You take their preimages and you intersect them, and that gives you back the subgroup sigma. So basically, if you have a group and you have a homomorphism to a residually finite group, then the kernel of that homomorphism is going to be separable. Okay, so that's an example of a separable subgroup. Okay, so locally extended residually finite then means that finally generated subgroups of G are separable. So the local here is just group theoretic terminology to mean finitely generated. We generally want to restrict to finitely generated subgroups because for infinitely generated subgroups, there's no hope in general of them being separable. Like you can take like a free group and you can surject it to an infinite simple group, and then the kernel can't possibly be separable. So we want to avoid infinitely generated subgroups in this concept, which is where the local comes in. So previously well-known examples include free abelian groups, free groups was proven by Hall in 49, surface groups was proven by Scott in 78, and then certain doubles of free groups were considered by Zhidek and Rips in 95. So I'm not going to explain precisely what the category was there. The Bianchi groups were proved by myself, Long, and Reed in 2001 to be Lerf. Certain other arithmetic subgroups of PSL2C, again, I haven't defined what an arithmetic means, but the Seifert-Weber dodecahedral space that I gave an example yesterday is such a, covered by the theorem, as well as the figure 8 knot complement. That's a special case of a Bianchi group, essentially, and that case was also proven by Donnie Wise around the same time, although his paper didn't appear until 2006. So Thurston's question number 15 is whether Clining groups are Lerf. Okay, well, why was Scott considering this concept? Scott and Hall, why did they consider this concept of Lerf? So, well, first of all, not all three-manifold groups are Lerf. For example, there's the fundamental group of this link complement's not Lerf. This was proved by Niblo and Wise in 2001. So if you take the Olympic rings, the fundamental group of the complement is not Lerf. So actually, the example here goes back to, I think, Baumslag and Solitar that came up with an example, and then it was sort of generalized by them. So we can't hope to prove Lerf for all three-manifold groups. Nevertheless, we can try to do it for certain classes of three-manifolds. So why are we interested in this? Well, Scott observed in 78 that what Lerf allows you to do is if you have a pi1 injective immersion, then you can lift it to an embedding in a finite sheeted covering space. So what I have in mind here is you have a three-manifold with some surface that's, well, as I explained yesterday, it's immersed, but it's just singular. It has lots of double points. But let's say it's in the covering space corresponding to its fundamental group. So this is a covering space that would be homotopy equivalent to the surface. Actually, from the tameness theorem, it follows that it's actually homeomorphic to the surface cross R, if this is our hyperbolic three-manifold, or actually in general, I guess. So you can get a nice embedded surface upstairs. And if this subgroup is separable, then that implies that there's a finite sheeted covering space in which the surface embeds in that finite sheeted cover. And so this finite sheeted covering space resolves the double intersections here. So there'll be other copies of the surface in the preimage of the surface up here, but we've separated this surface from the other components that will be upstairs. So and of course, this is obviously relevant to this virtual Haken question because we want to find a finite sheeted cover where this immersed surface then lifts to an embedding. So that's why Lerf is relevant and why I think Thurston asked this question in conjunction with the other three questions. All right, so so if M is a hyperbolic three-manifold and has Lerf fundamental, so this is what I was just saying, then we can, we now know from 2009 by these Kahn-Markovich theorem that there's these immersed surfaces inside the manifold, and then Lerf would allow us to lift them to an embedding in a finite sheet of covering space. And in fact, using an argument of Lubotsky, you can actually get a finite sheet of covering space with positive Betty number just from this Lerf criterion and when you have a surface. Okay, so that's why this separability notion is important in three-manifold topology. Now I want to talk about a different group theoretic condition that turns out to be relevant to virtual fibering. So first I need to define a sequence of subgroups of a group. So the rational derived series of a group is defined inductively as follows. So hopefully you're familiar with a derived series. So you take iterated commutators to get the derived series. So if G upper 1 is the commutator subgroup of G, so it's the subgroup generated by all commutators of elements in the group, then the rational commutator subgroup is you take any element that has some power that can be written as a product of commutators, and that's the rational commutator subgroup. So this G upper 1 clearly contains, G upper 1 sub r clearly contains G upper 1. And then you define these inductively by the nth rational derived subgroup is obtained from the n minus, or the n plus first is obtained from the nth by taking the rational derived subgroup of it. So it's kind of like taking the derived series, except we allow these powers. So why is it called rational derived series? Well, another way of stating it is you take the G modulo its commutator subgroup, and that's an abelian group, but then you tensor it with Q over Z, and that gets rid of all the torsion. And so that's why these x to the k's is sort of getting rid of the torsion in there. And we take the kernel of that, and that's the first rational derived subgroup. Or you can think of it as you're taking the kernel of the map of G to H1 of G with rational coefficients, which is equivalent. So these quotients then are going to be solvable groups because these G1 or GNR contains Gn, and the quotient of that is G mod Gn upper n is solvable. So a group G is called residually finite rationally solvable, or what I abbreviate as REFers, if there's a sequence of subgroups G equals G naught greater than G1, G2, whose intersection is trivial, so it's a co-final sequence, and they're all finite index subgroups of G, and each one contains the rational derived subgroup of the previous one. Okay, so this, for algebraists, maybe this, you can parse this, but underlying this algebraic definition is really a geometric picture. Just a remark, if we assume the GIs are normal in G, which you can do by taking the core of the subgroups, then the quotient G mod GI is a finite solvable group. So a residually finite group, recall, it means that any non-trivial element can be sent to non-trivial element in a finite quotient. It's residually finite solvable if you can do that in a finite solvable quotient. But this rationality criterion is a little stronger, and it may not be so clear why it's relevant. But in order for this series to even exist, you have to have non-trivial first Betty number to start. Let's say if it's a finitely generated group, then the first Betty number will be non-trivial. And so, so it's a pretty strong, so you already have to have something that has positive first Betty number for this to work. So one remark then, important remark, is that if G satisfies this REFers condition, then it's easy to see that any subgroup also inherits that property. You just intersect it with these, and you see that it works. So examples of REFers groups are, well, there's free groups, surface groups, z to the n, and free products of REFers groups are also REFers. So the geometric formulation of it is, if say you have a three-manifold with REFers fundamental group, then it's equivalent to saying there's a cofinal tower of finite index covers. So we have M, and it's covered by M1 and M2, and each of these has fundamental group, the G1 corresponding G2, et cetera, where fundamental group of M is G, such that Mi plus 1 is obtained from Mi by taking a finite sheeted cyclic cover dual to an embedded non-separating surface in Mi. So it's a very geometric condition. Maybe I should try to draw a picture of this. So the picture is you have your three manifold, which has this non-separating surface inside of it. And this is representing some positive first Bay number here, or non-trivial element in H upper 1 by Poincare duality. And then we're going to take a cyclic cover of it. So this is our Mi, and Mi plus 1 is obtained by taking a cyclic cover that's sort of dual to that surface. And then so we're going to see a bunch of copies of this surface upstairs. And this may not be a product in here. There might be some non-trivial topology going on here. If it were a product, we would already know that the manifold was fibering, although you can still consider this condition for fibered manifolds, of course. So that's the geometric condition for reefers, and this is where it came from. So equivalently, you have a homomorphism of pi1 mi to z, and then a finite cyclic quotient, and pi1 mi is the kernel of that map. So that's the algebraic way to say that. So maybe this is a better way to describe the reefers condition, but it's whatever your preference is. So this condition, as I alluded to, you have to start out with positive first Bay number, but actually, unless the group is an abelian group, then it'll have virtual infinite Betty number if this reefers conditions holds. So that's a fairly easy exercise in this statement. Okay, so what I proved in 2007 is that if you have an aspherical three manifold and its fundamental group satisfies this reefers condition, then it virtually fibers. In fact, well, one of these covers, Mi, these eventually become fibered after some stage. And I don't have an estimate on how far you have to go, although in principle one could make an estimate. So the proof makes use of Gabai's theory of sutured manifolds that I alluded to yesterday. It was this inductive technique to create foliations. So here we're sort of creating a foliation, but it's actually a foliation which is trivial. It's just a product of surface, surface crossed with a circle, essentially. Or a fibration, not just a foliation. So in fact, as I said, one of these covers, Mi, will fiber. So recently there's been a self-contained proof by Friedel and Kitayama that's appeared on the archive in October. So I'd recommend looking at that if you're interested in learning some of the details. Now, I wanted to point out that I announced this theorem at Thurston's birthday conference in 2007 here at Princeton. It was a different lecture hall, but at the time of the talk, though, I didn't know any examples of closed three manifolds or interesting three manifolds that had reefers fundamental group. I only knew it held for like free groups. So in particular, I didn't, didn't have any examples of closed three manifolds that were then virtually fibered from this condition. Although it does have interesting consequences for like handle bodies. So part of the goal of this talk then will be to discuss a general method for finding these reefers groups later on in the lecture. And this method I actually discovered while I was stuck at Philadelphia Airport on the way home from that conference. So turns out if you fly out of Philadelphia in a thunderstorm, then you have lower priority than the flights coming out of LaGuardia and JFK. So we were stuck on the tarmac for like 5 hours. Although I guess I discovered the theorem while sitting in the airport after my first flight had been canceled. So, okay, so now I'm on to the next topic. So I've talked about these three manifold group properties. Again, this is a highly selective set of properties that I'm discussing, which are not at all a survey of all the properties of three manifolds that you could consider. So now I want to go on to geometric group theory. So what is geometric group theory? So first I have to talk a little bit about Cayley graphs. So if you have a finely generated group, you choose some generating set G1 through Gn, then the Cayley graph on the generating set is a graph with gamma with vertex set G, and the edge set will be all pairs of elements which differ by one of the generators. So we take pairs G and G times Gi, where I runs 1 through n. So the degree of every vertex is 2n. So I'm not, you could consider this as a directed graph if you like, but I'm considering these as like symmetric pairs, so I probably should have written the other direction as well. So we can regard this graph then as a metric space just by letting the edges of the graph have length 1, and then take the path metric on the space, and that gives a metric on the Cayley graph. So the distance, if I know the distance from the identity element to G, then that's determined by you take the smallest product of generators or their inverses that gives you G. So it's the smallest case such that you can take a product GI1 through GIK, each one to some plus or minus 1, that gives me G. And then that's going to be the distance between the identity element and the vertex corresponding to G in the Cayley graph. And this notion of distance is clearly G equivariant under left multiplication. So if I take an element of h of G and I multiply on the left, then the distance of h to h times G is equal to the distance of 1 to G. So that tells you how to figure out the metric in general. Once you know the metric on the vertices, then you can also figure out the metric on the rest of the graph easily. Okay, so it's, this metric is left invariant under the action of G. So here's an example of a Cayley graph of the free group on 2 generators. You get this infinite tree, 4-valent tree, with respect to the 2 generating set A and B. Okay, so that's a classic example of a Cayley graph. Okay, so what is geometric group theory? Well, one origin of the subject, it actually has maybe several different origins, but geometric group theory is really the study of properties of groups by studying geometric properties of their Cayley graph. So geometric just means, well, it's a metric space, and so we can study a geometric property of it. This has some origins in the work of Dane on the word problem for surface groups, so that's sort of led into more combinatorial group theory, which is also related to geometric group theory. But really the origin of the subject might be Milner's paper in 1968, who studied the growth of balls in the Cayley graph of a group as a function of the radius. So what do I mean by that? Well, if you take the ball of radius r in the Cayley graph, where r is some integer, in the Cayley graph of a free group on 2 generators, then it has 1 plus 4 times 3 to the r minus 1 vertices. So if we go back to this picture, the ball of radius 0 has 1 point. The ball of radius 1 will have these 5 points. And then in each one after that, you get 3 more vertices adjacent to the outermost guy there. And so it multiplies by 3 from then on. Is that clear? And so the growth of this is exponential. It's 3 to some power. So we say that this group has exponential growth, and so Milner in his paper, he proved some other things, but one thing he proved is that a group has exponential growth with respect to one generating set, then it'll have exponential growth with respect to any other generating set. The growth, the constant of growth, the base of the logarithm or whatever, the exponent, might be different for different generating sets. But it's independent, the fact that it's exponential is independent of the generating set. He also considered groups of polynomial growth and other concepts. Now, that's one aspect of geometric group theory, but we can also consider a group G that acts properly and co-compactly on a metric space X. So just think of like a compact manifold, and the metric space is the universal cover, compact Riemannian manifold, say, or just a compact metric space. And G is the fundamental group of that. Then it'll act on the universal cover. Then some of the geometric properties of X are reflected in the geometric properties of the Cayley graph. And so we can study the properties of a group by studying the geometric properties of X. And then some of those translate into the geometric properties of the Cayley graph. And so, for example, Milner showed that if the volumes of the balls of radius r in X grow exponentially with r, then the same will hold for the balls in gamma. Of course, what do I mean by the volume of the ball in gamma? I just mean the number of vertices in the ball, or whatever you like. So, so exponential growth of balls holds for universal cover as a compact Riemannian manifolds with negative curvature, like hyperbolic manifolds. Now, a little bit later, Cannon in '84 realized that the Cayley graphs of hyperbolic manifolds, not only do they have this exponential growth, but they have a very nice sort of combinatorial recursive structure for constructing them. And that eventually evolved into the theory of automatic groups, which is another another topic in geometric group theory. And then this notion, this sort of things that Cannon was thinking about were sort of extended and codified at Gromov in '87 in the notion of a hyperbolic group. So there's, he has a famous preprint that that's called Hyperbolic Groups, and it's got hundreds and hundreds of citations. So that's what I want to describe now. So Gromov hyperbolic metric space, geodesic metric space. So what do I mean by geodesic metric space? Is that clear? What does that mean? Does anyone have an idea? Well, so what's a geodesic? So if you have 2 points and you have an arc between them, then inside of the metric space, then it's parameterized by arc length. So the distance from any, so in a geodesic, you have the property that any point x on there, the distance of A to x plus the distance of x to B is equal to the distance of A to B. So this is a geodesic. It's a map of an interval with endpoints A and B that satisfies this property, right? It's clear that x is sort of in between A and B in this sense. It's the triangle inequality. Your triangle is degenerate to a line. Okay, so a geodesic metric space has the property that any 2 points are connected by a geodesic. And it's easy to see that a Cayley graph, for example, is a geodesic metric space, just because, well, all the distances between vertices are integers, so there's some smallest integer, and then you just take the path that satisfies that. Okay, so for a geodesic metric space, then this Gromov hyperbolic notion can be defined in the most simple way by Rip's thin triangle condition. So for points A and B in the metric space, I'll just denote the geodesic as the interval from A to B. Of course, that's not unique, but you could also just take all of the geodesics between A and B if you like. Then X is called delta hyperbolic metric space if for any 3 points A, B, and C in X, the interval between B and C, the geodesic between B and C is contained in a delta neighborhood, so I'm using n delta to imply you take the sort of delta tubular neighborhood, all the points that are distance delta away or less from this set of A, B, union AC. So you have this triangle. So Euclidean space is not delta hyperbolic. I can take a triangle there, and for any given delta, I can just expand this triangle until the delta neighborhood of these two sides doesn't contain the third side. So Euclidean spaces are not delta hyperbolic. Trees are delta hyperbolic. What's the delta constant in this case? So I have here's the geodesic between A and B. Here's the geodesic between A and C. Here's the geodesic between B and C. That's contained in some delta neighborhood of the union of these other two. And what's delta in that case? Zero, yeah, it's actually contained in the union of the two geodesics. So this is sort of the best example of a delta hyperbolic space. So it's zero hyperbolic, and you can see that's essentially equivalent to being a tree. Here's a delta hyperbolic space where I have an edge of a triangle here, an edge of a triangle here, an edge of a triangle here, and this edge will be contained, and I take a tubular neighborhood around this edge and around this one, and it contains this third one. Okay, so that's Rip's thin triangle, delta thin triangle condition. So, for example, hyperbolic space is delta hyperbolic with the constant delta equal log of 1 plus square root of 2. That's an easy hyperbolic geometry computation. So a group is called delta hyperbolic if for some generating set you take its Cayley graph, and that's a delta hyperbolic metric space. That's a geodesic metric space. And if the triangles are all delta thin for every single triangle in the metric space, so it's a global condition, then G is called a Gromov hyperbolic group. So trivially then, finite groups are Gromov hyperbolic because, well, if you take the Cayley graph of a finite group, it's got bounded diameter, whatever that diameter is, D say, then every triangle will be D thin, because when you take the D neighborhood, you get all the points in the space. So that's kind of a trivial example. But Gromov proved many nice properties of these groups, and I'll just mention one of them. There's a compactification of the Cayley graph with a boundary at infinity. And what this boundary is, you take all geodesic rays in the Cayley graph going off to infinity, and you put a certain equivalence relation on them. If they stay bounded distance from each other, then they form an equivalence class. You can check that's a well-defined equivalence relation.
So if you find out volume hyperbolic
yeah.
group, a finite volume hyperbolic manifold, you take the fundamental group, it's not uniformly hyperbolic. Does it fit into this?
Yeah, I was about to mention that, yeah. So if you take a compact hyperbolic manifold, then its fundamental group will be delta hyperbolic for some delta.
And if it's finite volume, it's not.
Oh, if it's finite volume, that's right. It's not going to be. That's right. So and it turns out this boundary at infinity is independent of your Cayley graph gamma. So it's independent of which generators you chose. So going back to our free group example, if you try to draw it, then you sort of see the Gromov boundary appearing as this fractal, which is really just a Cantor set off at infinity here. And that, if I chose a different generating set here, I would still get the same boundary at infinity. And this is quite important for analyzing like the cohomological properties of these hyperbolic groups and various things. So now I need to talk about another notion introduced by Gromov of a quasi-convex subgroup. So we'll take G to be a hyperbolic group with Cayley graph gamma. And a subgroup can be regarded as a subspace of the Cayley graph just by taking the vertex set of that subgroup. Then it's called quasi-convex, 2k plus 1 quasi-convex, if for any element in H, and you take some geodesic connecting 1 to the H, then that's contained in a 2k plus 1 neighborhood of the subset H. So here, this is sort of a cartoon picture. H is represented by this plane here. The geodesic is going outside of H, but it's staying within a 2k plus 1 neighborhood of that. So if it was convex, then that would be, your constant here is 0. But the quasi is saying you got a little leeway. Your geodesics don't have to stay inside the subspace. They just stay a bounded distance away from it. And we say then that H is a quasi-convex subgroup of G if it's 2k plus 1 quasi-convex for some generating set. It's a basic fact in Gromov's theory that this notion is independent of which generating set you take. This follows from what's called the stability of quasi-geodesics, but I don't really have time to get into the details of that today. So what are the motivating examples of hyperbolic groups? Well, for me, they're Clining groups, although as Peter just alluded to, they're the ones without the z-squared subgroups. So it turns out that in a hyperbolic group, every billion subgroup is up to finite index just z. You can have a little bit of torsion, because you can always cross, say, Z with a finite group. Z is a delta hyperbolic group, because the line is delta hyperbolic. So the fundamental groups, the closed hyperbolic manifolds are delta hyperbolic, but if you take a cusp hyperbolic manifold like the figure 8 knot complement, then its fundamental group is not delta hyperbolic, strictly in this sense. Some motivating examples of quasi-convex subgroups then are these quasi-Fuchsian groups, these surface groups such as the Kahn-Markovich groups that I mentioned yesterday that have limit set, they fix the circle on the sphere at infinity. Oh, and I forgot to say that for these hyperbolic free manifolds, for example, their sphere at infinity, since it's independent of which generating set you choose, well, it's actually independent of which space you choose. So it's just the boundary at infinity of hyperbolic space. If you take this Gromov boundary of hyperbolic space, you get the sphere that compactifies it to a ball. So, those are examples of quasi-convex subgroups. So here's a theorem that I proved with Pedrosa and Manning took care of the cusp case. If hyperbolic groups are residually finite, then Clining groups are locally extended residually finite. So we were interested in this question of whether Clining groups are Lerf because of the obvious relevance to the virtual Haken question. But this hypothesis here is a very big hypothesis. Hyperbolic groups are residually finite. Well, so this is one approach to maybe showing that hyperbolic three-manifold groups are Lerf, and then approach to showing the virtual Haken question. But the caveat here is that it's believed by the experts in geometric group theory or in hyperbolic groups that there's non-residually finite Gromov hyperbolic groups. In fact, there's examples of nonlinear Gromov hyperbolic groups. So that's a little bit of evidence that there might be ones that are not residually finite. But there's no method, I mean, there's not really that many good methods for producing residual finiteness. And one of Donnie Wise's big breakthroughs is to sort of realize general techniques for creating residual finiteness. Okay, so now I need to talk about another topic that Gromov introduced, and I apologize for all the definitions. Most of this talk today is going to be definitions, but to explain the transition from the three-manifold world to the geometric group theory world, I have to explain some of these concepts. So, or is there any questions so far on the notion of hyperbolic groups or quasi-convex subgroups or any of this stuff? Okay, so now I want to talk about cube complexes. So a topological space X is a locally cat-zero cube complex, or locally is a cat-zero cubed. If it's a cube complex, so it's just like a simplicial complex, but it's made out of cubes. These are any-dimensional cubes. And when you put the standard Euclidean metric on each cube, then it gives what's called a locally cat-zero metric. So I'm not going to explain precisely the notion of a cat-zero metric. That stands for Karateodori Alexandrov Toponogov, I think. Or no, yeah, that's right. So, what Gromov realized in the same paper on hyperbolic groups in '87 is that this condition of this non-positive curvature condition is equivalent to a purely combinatorial condition on the links of the vertices of the cube complex. And these are, the links of the vertices are flag complexes, flag simplicial complexes. So maybe I should say what the link of a vertex is. If you have actually any polyhedral complex, but in particular a cube complex, then the link of a vertex is you take, well, if I think of this as like a Euclidean cube, I just take a little boundary of an epsilon neighborhood around there. And when you take this and you intersect it with a little sphere, you're going to get a right-angled spherical simplex. And then I can, if I have another cube glued on here, then I can extend this to get a simplicial complex. So here the link is just an edge together with a triangle. So that's the link of a vertex in a cube complex. It's a simplicial complex. So the claim that Gromov made is that this metric condition that I'm not explaining is equivalent to this purely combinatorial condition that the links of the vertices are flag complexes. I also wanted to mention that in these cube complexes, there are these hyperplanes. So I can take a cube and I can cut it in half by a midplane. And there's a unique way to extend that into each next cube. Now, the dimensions of the cube might change and they might terminate or something, but there's a unique way to extend it. Now, be aware, though, that this does not give an embedded subcomplex. It only gives a sort of locally embedded subcomplex because this complex might extend around and come back and intersect itself, and you might get some self-intersection. So like here, maybe this guy extends around and comes back to self-intersect, and then these hyperplanes then will not be embedded. But I want to think of, so the immersed cube complex here is going to look like there's going to be a square at one end and a square at another end. And so the mapping is not embedding because there's this line of double points that, where these two squares intersect. So I don't want to sort of glue those guys together. I want to think of them as there's this map from this complex into the cube complex of a higher dimension. So those are called the walls or the hyperplanes, and so we'll see why they're relevant in just a sec. So I wanted to get back to this flag condition, though. So what are some examples of cat-0 cube complexes? Well, a square complex, so that's just a two-dimensional cube complex, has the property that it's cat-0 if and only if the length of each vertex is a graph of girth greater than or equal to 4. So here's an example of squares tiling the hyperbolic plane. This is in the, say, in the Clining metric, since these are straight. And you see that the length of each vertex is a graph with of 5 edges. So, so this is a cat-0 square complex. If we were to make these out of Euclidean squares instead of hyperbolic squares, then it would satisfy Gromov's condition. Now, there's also these walls I just mentioned. So the sort of dual picture, so along each of these families of squares, we can take the midplanes and amalgamate them together, and you get these nice geodesic arcs in the hyperbolic space. So these midplanes give you sort of a version of Poincare duality, at least if you happen to be a manifold. So back to the flag condition. So this is a picture I stole from Rob Grice. So here's a cube. Here's the length of the vertex. Anytime you see a 3-cycle in the length of the vertex, there has to be a triangle that fills it in. More generally, if you see the edges of a K-simplex, namely a K+1 clique in the one skeleton of the length of the vertex, then there actually has to be a K-simplex that fills it in. So that's why on the previous example, in the two-dimensional case, the graph, you can't have a 3-cycle, because then there would have to be a triangle that fills it in, which would have to be a cube like we saw over here. So it would have to be 3-dimensional instead of 2-dimensional. So that's why this graph, girth of the graph is greater than or equal to 4 is equivalent to being flag for a graph, for a one-dimensional complex. So a flag simplicial complex is determined by its one skeleton. You just throw in a K+1 simplex, K-simplex for every K+1 clique in the graph. So I'm going to take this Gromov's definition as the working definition for this talk, so I don't have to get into the geometric notions as much. So a topological space now we'll say is cubulated if its homotopy equivalent to a compact cat-0 cube complex. You can forget about homotopy equivalence. It just means that the fundamental group of Y, well, Y is aspherical, and its fundamental group is equal to the fundamental group of some abstract locally cat-0 cube complex. So I don't really care that it's a homotopy equivalence, just it's something that's giving me a different model for the fundamental group. And so I'll be interested in 3 manifolds which are cubulated. And one remark, these cubulations, there's 3 manifolds that are not homeomorphic to a cat-0 cubed, locally cat-0 cubed metric space. So this was proved by Tao Li, that there's certain 3 manifolds that you can't get some nice decomposition into cat-0 cubes. Now, there's a theorem of Sagiev in his thesis from UC Berkeley in 1995, which associates to a surface, immersed essential surface in a 3 manifold. It'll have one of those if and only if it acts co-compactly on a global cat-0 cube complex. So global cat-0 cube complex means that it's simply connected and locally cat-0. So if I don't have this sort of non-trivial topology like I drew over here, if it's simply connected, then it'll actually be globally cat-0. Again, we can just take this as to be the definition of. So what Sagiev's construction does is it gives a cube complex in which these hyperplanes, well, there's a group action so this cube complex extends in all directions, and there's a group acting on it. And the stabilizers of the hyperplanes will correspond to these surfaces, these immersed surfaces that are in the manifold. Maybe I can go back to my pictures here. So if I look at the stabilizer of one of these hyperplanes here, the quotient of this will be some surface by some, so say we have a group acting co-compactly on here. The stabilizer of one of these lines is just going to be a circle. So it's a codimension 1 object inside of that surface. It's one dimension inside of a 2-dimensional surface. So similarly, if you have a two-dimensional thing inside of a three-dimensional space, then the stabilizer will give you a hyperplane. So this also generalized various theorems. Sagiev's theorem can be pretty well understood if you have a geometrically infinite surface. There you get a crystallographic group action, or even more specifically, if you have a three-manifold fibering over the circle, well, now pretend this is a fibering. What does Sagiev's construction give here? Well, it's really, again, just a form of Poincare duality where the cube complex is really just a circle. So there's that intersects the surface in a single point. And so you get an action of the fundamental group on a line just by translation by z, and the quotient's a circle. So that's what Sagiev's construction gives in the fibered case. For an embedded quasi-Fuchsian surface, you actually get an action on a tree. And it's the sort of thing that has been studied by topologists for many years. So there's a theorem then of Bergeron and Weiss in 2009 that closed hyperbolic three-manifolds are cubulated. So there's a corresponding cube complex. Again, it might be much higher dimensional, but it's homotopy equivalent to the three-manifold. And the theorem makes use of these surfaces of Kahn-Markovich that I mentioned, which are sufficient to meet every geodesic in M and then give rise to cubulation. So what I mean by that is, for every geodesic in hyperbolic space, Kahn-Markovich can provide, well, they can, for any circle separating the endpoints, they can provide a quasi-Fuchsian group which gets very close to that. So well, this is not close to a circle, but here's a quasi-Fuchsian group that separates the two endpoints. And corresponding to this, so the surface was actually represented by, the universal cover is represented by some plane in hyperbolic space. And Sagiev's construction then gives you a hyperplane that's when the that element in the fundamental group, if this corresponds to the stabilizer, the axis of an element of the fundamental group, then it'll take this surface off of itself, and so you get a proper action on the cube complex. I mean, I haven't explained Sagiev's construction, but that's sort of morally what's happening. There's this north-south dynamics where, as you iterate a stabilizer of this geodesic, then the surface gets contracted down to one of the stable fixed points. And so that translates into a proper action. And when you have a proper co-compact action, then the quotient will be homotopy equivalent to the manifold. So that's where that theorem comes from. There's many known examples of cubulated hyperbolic manifolds before this theorem, like Aitchison and Rubenstein did the alternating link complements, if you're familiar with those. Another example comes from this famous picture of the cover of Bill Thurston's book on three-dimensional manifolds. So if we have a tessellation of hyperbolic space by hyperbolic polyhedra, then you can see the walls of the cube complex here. Do you see these sort of, like this circle kind of here? There's a plane, a totally geodesic plane that goes through there, and there's all these totally geodesic planes that go through in various directions. And so the dual to that is a cube complex. So the sort of Poincare dual around this corner here, there will be a cube. So you stick a vertex in the middle, you take the Poincare dual picture, and that will be a cube complex structure on hyperbolic space. So this comes from a right-angled dodecahedron. But any right-angled polyhedron in hyperbolic space will give you rise to a hyperbolic manifold or a tessellation by right-angled polyhedra, which is going to be dual to a cube structure on the manifold. But as I said before, you can't expect something that's going to be three-dimensional like we have in this case in the general case. But this is just to give you an idea of what these cube complexes can look like. So it turns out for this theory that the walls are more important than the cubes. Okay, so now I want to talk about a special sort of cube complexes that comes from these right-angled Artin groups. So a right-angled Artin group is you take a simplicial graph and you associate a group, a very simple group, which the nodes of the group are, the nodes of the graph give the generators for the group. And we have a relator, if two nodes of the graph, two vertices of the graph are connected by an edge, then we say that those two generators commute. So these are groups of the very simplest sort of presentations you can imagine. So if I take the trivial graph, There's no edges, there's no relations then, and therefore it's just a free group on those generators. If I take the complete graph, then that means every generator commutes with every other generator, and I just get the free abelian group. So these right-angled Artin groups sort of translate between free groups and free abelian groups. Like here, I get a free product of z squared and the free group on 3 generators. This one corresponds to the fundamental group of a 3 manifold. This is related to that Olympic rings picture I had. Here's another. This one, if you take a join of 2 trivial graphs, then you get a product of free groups, or more generally, a join of 2 graphs, you get a product of those right-angled Artin groups. So it's closed, these groups are closed when you're taking products. And actually, there's lots of 3 manifold groups that occur if you have a graph that's a tree or a triangle. So what group, so a triangle is just a complete graph, so that's the fundamental group of the 3 torus, Z3, which is the 3 manifold group. So associated to these right-angled Artin groups, there's a very nice cube complex. So the one skeleton is, well, I just take a wedge of circles, one for each vertex of the graph, and I put in a torus. So every time I see a commutator, I just throw in a commutator relator there, and that gives me a torus. And if I have a click in the graph, then I'm going to throw in a k-click, and I'm going to throw in a k-cube. But it's actually going to be a torus because the opposite sides will be identified since these edges are all have the same vertex. So it's just a union of a bunch of tori. So every click in the graph, you throw in a torus. Now, the nice thing about this Salvetti complex for the right-angled Artin group is that the links of the vertices will satisfy this flag condition. They're very closely related to the original graph you started with, where you double each vertex and do a little. Anyways, you can check that they're flag simplistic complexes. And therefore, these complexes are locally cat-0 cube complexes. So if you want an example, this is a huge class of examples of locally cat-0 cube complexes. So for the free group, you just get the wedge of circles. For the free abelian group, you're going to get the n torus. So you have the click as the entire graph, and so you throw in the n torus. For this guy, you take a torus, and you take one circle on it, and you identify it with a circle on another torus, and you take another circle that intersects in a single point, and you identify it with a circle of another torus. Turns out you can thicken this up and form a link complement. So this gives you a 3-manifold group, a 3-manifold with boundary. So those are some examples of right-angled Artin groups. Now, why do I care about right-angled Artin groups? Well, there's this notion then of a special cube complex, which is introduced by Haken and Wise. So the hyperplanes in special cube complexes are embedded. So you don't see this kind of thing where a hyperplane goes around and comes and intersects itself. They're embedded and two-sided. And moreover, there's a couple other conditions that say that there's no hyperplanes don't oscillate. So if I follow a hyperplane around, then it doesn't come back and sort of have a tangency here where, so a hyperplane can be thought of as an equivalence relation of edges that share opposite sides of a square. And under this equivalence relation, I don't get an edge that, 2 edges that share a common vertex or common endpoint of the same orientation, of opposite orientation. And there's no interosculating hyperplane. So here I have a hyperplane, here I have a hyperplane that cross at this square, but here they're sort of tangent to each other, or the edges share a common vertex. And so these are forbidden in a special cube complex. So Haken and Wise introduced this, and so the motivating example are these Salvetti complexes of right-angled Artin groups. You can check that they have these embedded hyperplanes. You get a hyperplane for each generator in the group. And these hyperplanes don't oscillate or interosculate. So it's not too hard to check that Salvetti complexes of right-angled Artin groups are special cube complexes. So the theorem of Haken and Wise, 2007, is that if X is a special cube complex with hyperbolic fundamental group in the sense of Gromov, so hyperbolic, it's delta hyperbolic for some delta, the universal cover of this right-angled Artin group, the Salvetti complex associated with the of the special cube complex will be a hyperbolic group. Then the fundamental group of the special cube complex embeds in a right-angled Artin group, And the quasi-convex subgroups of pi 1x are separable. So, so in other words, we can get some form of Lerf, not for all finely generated subgroups, but at least the quasi-convex ones. So for the proof, well, how do you get a right-angled Artin group? Well, you take a graph that has a node for each embedded wall of X. So all the walls each component of the wall is embedded. And you take an edge when two walls cross each other. So that gives you a graph, and you take the associated right-angled Artin group in the Salvetti complex, and what they prove, there's a very nice localized symmetry from the special cube complex to the Salvetti complex of that right-angled Artin group associated to the crossing graph. And that's a local, you can show that it's a localized symmetric immersion and when X is special, and then, then if it's a localized symmetry, then you get an injection of fundamental groups. So it's sort of a local to global or geometric way of injecting one group into another group. So what happens, for example, I said the Salvetti complexes are special cube complexes. What happens if I apply this construction to a Salvetti complex? Well, it just recovers that right-angled Artin group that you started out with and the Salvetti complex, and this localized symmetry is actually just a homeomorphism, or it's a metric localized symmetry. And so, so that's a special case of their theorem. But what they realized is that if you look at complexes which locally isometrically immerse in a Salvetti complex, then going back to this osculating condition, these conditions are necessarily satisfied by any, so if you have a special cube complex, any cover it's easy to see will also be special. So if you want to locally isometrically immerse into a special cube complex like a Salvetti complex, then you already better be special. But what they realize is that the converse is true, that if you don't have these obstructions to embedding, then you actually can embed, which is kind of remarkable. So this whole theory of special cube complexes, it's maybe a little hard to sort of parse why these conditions of osculating and interosculating are important, but they sort of forced upon you by trying to locally isometrically immerse into a Salvetti complex. So the geometry sort of guides you here to the right theorem. Now, why are these subgroups separable? I wanted to make one comment about separability in this case. Again, the separability is proved in a very geometric fashion, as opposed to the separability of the fibered case that I described. So a subgroup is called a retract if there's a retract, so it's a homomorphism that's the identity on the subgroup, and it's a virtual retract is a finite index subgroup that retracts to the subgroup. So L has to be a subgroup of G prime, which is finite index in G, and then there's a retract onto that subgroup. So what's an example of a retract? Well, if I take a graph and I take a subgraph that's spanned by its vertices, so it's, you take a subset of vertices and take all the edges that connect those vertices, that's a spanned subgraph. Then there's a natural retract from the Artin group on that larger graph to the Artin group of the subgraph just by setting the generators which are not in that subgraph equal to 1. So like if you have z to the n, then it has a retract on an a z to the n minus 1 by just deleting a vertex from your graph. Or if you have a free group, it has a retract onto any generated by n elements. I just throw out some subset of them, and it'll retract onto what's left just by sending all those generators to the trivial element. So the claim is that if you have a residually finite group and you have a subgroup that's a virtual retract, then it's separable. So this is a nice elementary exercise in residual finiteness. Actually, it's easiest to prove this using what's called the profinite topology, but I didn't want to get into that today. But anyways, Hagen proved that quasi-convex subgroups of right-angled Artin groups, or rather, I should have said here, special cube complexes with hyperbolic fundamental group are virtual retracts. And this is proved in a very geometric way, a combinatorial way, using what's called canonical completions and canonical retracts. It's essentially a geometric or combinatorial version of a convex hull. And then the retract comes in a very similar, it's really just a generalization of this example here. So if you understand this example, right-angled Artin group retracts, then this canonical completion and canonical retract is just an extension of that to special cube complexes in general. In fact, if you do this whole construction, then it's just a specialization of the retract here, it turns out, to the retract here under, if L is sort of a geometric subcomplex. Okay, so now we go back to the fibering criterion. Let's see, how much, oh, am I already over time? Sorry about that. I think this is my last slide, or second to last slide. So if M is virtually special cubulated, then M is virtually fibered. So if you have a cubulated manifold, then there's a finite sheet of cover that's special, and that implies that it's this finite index subgroup or finite index cover of the manifold will be a subgroup of a right-angled Artin group. Now, right-angled Artin groups are reefers, and so it passes to this subgroup, and then my reefers condition implies that it's virtually fibered. So this is what I discovered at Philadelphia Airport, that these right-angled Artin groups are reefers. And together with this theorem of Kahn-Markovich and Bergeron-Wise, this implies that we only need to show that the fundamental group is Lerf to show that it's virtually fibered. You can show that if you have a cube complex with Lerf fundamental group, then it's virtually special. So what Wise proved in 2011 is that Haken hyperbolic three manifolds are virtually special cubulated. And thus, they're virtually fibered. So Wise's theorem gives a different approach to finding cubulations than the one I mentioned before, Bergeron-Wise. And the proof of his theorem is a 185-page preprint. It also makes use of some work of Hagen and Wise, which was published just this year in the Annals, and a preprint of Xu and Wise, which is another 60 pages or so. So it's a pretty significant contribution that he's been working on for many years. And Wise conjectured in his result that cubulations with hyperbolic fundamental group are virtually special. The subtlety of this conjecture is made apparent by a theorem of Berger and Moses in 1997 that says the fundamental group of a locally cat-zero square complex, there's examples which are simple and whose universal cover is a product of two regular trees, finite valence regular trees. So this is a cat-zero square complex with simple fundamental group. So it can't possibly be residually finite or have any of these other properties. Sorry about that. In particular, the universal cover is isometric to a product of two free groups. The universal cover is a Cayley graph of free groups. And so it looks like a product of two free groups, which is residually finite and all that. So I proved Wise's conjecture earlier this year, and that by all what I've explained so far in these talks, that implies that the fundamental group of a closed hyperbolic three manifold is Lerf. It virtually fibers, and it's large, meaning there's a finite sheeted cover whose fundamental group surjects a free group with two generators. And so this resolves Thurston's questions. And the proof, it makes extensive use of Wise's results that I'm going to try to describe tomorrow, or on Thursday. So also, I want to mention, or I'll talk more about it, that there's a separability result that I proved with Groves and Manning that's in the appendix to my paper, and I'll hopefully talk about that on Thursday. So the goal of the third lecture will be to describe Wise's work, and then how I apply his results to actually prove his conjecture, together with some new ideas. So I apologize for going over today. So stop there.